Good afternoon. Thank you for coming. My name is Cody Chiuzan. I'm an assistant professor in the Department of Biostatistics and the director of the educational initiative of Biostatistics, Epidemiology, Research and Design, sponsored by CTSA, the resource that's actually bringing all these monthly lectures. And I'm actually today going to be the presenter of practical tutorial about propensity score matching. So the main goal is to introduce you to some ways of adjusting for confounders when estimating the effect of a cause or an intervention. I will start with a brief definition and comparison between experimental and non-experimental studies that will pretty much justify the use of propensity score matching. Then talk about the treatment selection, treatment outcome and covariate selection, the models that can be used to actually generate the propensity scores, and you'll find out what those are, and methods for analyzing the outcomes after doing the matching. At the end of the presentation, I included an example from a paper, from a retrospective study that I worked on, to show you how we reported the results, how we assessed propensity score matching, and give you some standard language of how to write. At any point, if you have a question, please feel free to ask. So what's the main idea of propensity score matching? Propensity scores methods allow for causal inferences from non-experimental studies. Research studies pretty much fall into two categories: experimental, interventional, and non-experimental. Some statisticians don't like to call them observational because all studies collect observation. All of them are observational. So interventional versus non-interventional, meaning does the investigator has control over the intervention, over the independent variables, yes or no? But to use the term that we are so used to, observational studies also have the goal of understanding a cause-effect relationship, even if the independent variable is not under control. Now, at this point, I want to underline the difference between inferences about association and causal inferences. We're all familiar with associations, association between two variables, between independent and dependent. Now, causal relationship is a little bit more, involves different aspects. A causal relationship, it's not only, does not only involve a very high correlation or a strong association between the variables, but it also involves a temporal component, meaning the cause must precede the effect in time, and a correlation association are not by coincidence alone. Causal inference pretty much assess the response of an effect when the cause is changed. B is caused by A, and you want to see how the effect changes if E is also modified. In experimental studies, in interventional studies, clinical trials, we already know that the standard, the norm for outcome evaluation is randomization. Why is randomization so useful? Because of two main reasons. One is minimizes bias, selection bias, accidental bias. And the second, very, very important, that I want to underline is randomization makes the groups comparable. Comparable to what? Comparable with regard to observed or unobserved confounding. Because at the end of the day, you want, if you detect an effect and if one truly exists, you want to make sure that the difference in outcome between the groups is purely due to that effect and not because of underlying confounding. But that's in interventional. What do we do in non-experimental studies? What do we do in this observational? How do we guard against this bias? One, we can do stratification. Meaning, we take several variables that we know that the groups are different with respect to, and we split them into categories. Now, that's okay, absolutely, if you have one or two variables, but think about if you have like 3 variables, each variable having 3 categories. 3 times 3 times 3 times 3 takes you to 27 cells, 27 categories that you have to group your data. If it's a big data set, that's fine. If it's a small data set, that you might end up with a very small number of subjects in one category. So that's not always feasible. A second option, if stratification is not an idea, is use regression. Everybody heard of linear regression, logistic regression, adjusted analysis, where you adjust for all kinds of covariates. That's fine. As long, again, as you have a good sample size, but you have to be careful. These regression models also come with a lot of assumptions that are all pretty much remain unchecked. Linearity, different distribution of residuals, and even an equal distribution of confounders across the treatment groups. So if stratification, regression are not feasible options, then let's try matching methods. Matching methods are used in observational studies to try to fix, as much as possible, the lack of randomization. What's very important to know that propensity score matching involves a modeling of this propensity scores that can be conducted independently of the outcome analysis, meaning that you have some protection against the model fit. Okay, so what do we do? What are the steps in propensity score matching? Number 1, identify an appropriate data, appropriate and sufficiently large. When we do the matching, we want to make sure that we have enough subjects in the groups to be compared, so you can do the matching. What is a sufficiently large sample size? Towards the end of the presentation, I recommended at least 200 subjects in total. Second, define the treatment and control, or the reference group, and the outcome that you are interested. So remember that in observational, we do not have your treatment and control predefined as you have them in interventional or experimental studies. So you have to decide what groups do you want to compare? What groups are you interested? And one is going to be the comparator, and one is going to be the reference. After you decide on your groups, very important, you have to select the covariates of interest. What does it matter? In propensity score, the main goal is to make the groups comparable. Comparable with respect to a lot of observed confounders. And those confounders are the covariates of interest. What do you think? Where do you think the differences may lie? Is there a difference in gender? Is there a difference in age? You have to consider these covariates before you do the matching. Then you fit a model, you get your propensity scores, and you match. You've tried to match one subject from your comparator group with one subject from your reference. No, I don't want to call placebo because it's not correct. You create your pairs, and then you go ahead to step number 2, and you look at the outcomes, and then you can compare the outcomes. Once the groups are comparable, then you can assess the final outcome, which is actually the ultimate goal. Step 6 and 7 are also important because matching should not be a black box. It's not a software that you run on SPSS or SAS, or they found these pairs, you're done. You have to assess. Have you done a good job matching? How do you assess that? You compare the groups before and after, and you want to see if the imbalance between the groups has been taken care of. If that looks okay, then you might have some valid inferences. Any questions so far? So let's talk about treatment and outcome. How do we select our groups, the groups to be compared, the groups to be matched? One is called the treatment or the intervention, and the other one is, and the others can be your reference groups. Some examples. Let's say you want to compare males and females. These are the two arms. Then you're going to make male. You can make male the treatment or the intervention, and compare relative to females. Or another example, right, in your observational study, maybe you want to compare heavy drug users to something else, to a reference. What would that reference, what can that reference be? You have to decide. You can have absolutely no drug use, or you can have light or moderate drug users. So it's important right at the beginning to decide what groups do you want to compare. When the groups are defined, then you have to go to step number 2 and decide what do you want to compare them with respect to. What is your outcome? So let's say in our example, you have two groups, heavy and light drug users. These are the groups. You want to compare them with respect to mental health outcomes, such as, I don't know, the number of suicides in a year or the rates. But these are the two important aspects that you have to consider. Ideally, the treatment, the groups are measured absolutely for all individuals, treatment, covariates, and outcome. But in terms for causality, you would want ideally the treatment, the groups, to be measured before the outcome. That might or might not be possible in observational. Why? Because you don't really, it's very hard to establish temporality in observational studies. The fact that you decided that gender, male and females, are your treatment and are your treatment groups, that doesn't really involve a time point. Now, everything that I'm saying today, all the analysis is done at the individual level, meaning the treatment, the intervention, the outcome are all for one subject. But you can also have group-level treatments. What does it mean? Maybe you want to assess the effect on a different unit, like a school or a group of subjects. In that case, there is another multi-level approach to propensity score matching that you should know, but this is not what we're covering at this point. So after you decided the treatment, what covariates? What is your covariate selection? You want the groups to be comparable with respect to what? Maybe from the literature, maybe from your previous research or experience, you have identified some confounders, some variables that are different between the treatment groups. If you do have some prior information and prior knowledge, please go ahead and include those covariates. If you're not always sure, should you include or you should not include, what should you do? My advice is to include them, because propensity score matching does not penalize you for a big number of variables, as long, of course, as you have a good sample size. Go ahead and include as many covariates as possible, because the main goal is not model estimate, it's not predictability. You're trying to make the groups comparable as much as possible. If you have a good sample size, just stuck them in there. What would be a downside if you put too many covariates? Well, it might be very difficult to match and to find a match for your control. But I would say start with a larger set of covariates and then start reducing if you can find good pairs or you see that the sample size is drastically reduced. What covariates should you include? One, those that are related to the treatment. And secondly, that's a second objective is covariates that are related to the outcomes. Why is that? Because at the end of the day, propensity score matching, the propensity score model that you are going to fit is going to be a model where your outcome, the dependent variable, is the treatment assignment. Remember, the treatment assignment, we had males versus females, or we had heavy users versus light users. That's on your left-hand side. If you have two treatment groups, then you have a binary outcome. What is the most common model that we use for modeling a binary outcome? Logistic regression. So think of this. Wrap your head around this, and you have a logistic regression with the outcome being the two arms, males or females. On the right side, as for covariates and independent variables, you have all those covariates that you want to match, for. So when you fit a logistic regression, right, what do you get from a logistic regression? Everybody's familiar with the concept of odds, right? But we're pretty much modeling the log odds. What goes into the odds? Probabilities. Odds is P divided by 1 minus P. Well, surprise. Propensity scores are probabilities. At the end of the day, in a logistic regression, that's the most common method for PSM. Each subject is going to have a predicted probability of receiving treatment. Those are the propensity scores. So imagine you have 200 subjects. The model gets you, after feeding the model, you get predicted probabilities for all these subjects. And that's where it starts. Because now, based on these probabilities that go from 0 to 1, you're going to match the treatment group with those from the reference, from the control group. So this is propensity score matching. What happens if you have more than 2 groups that you want to compare? For 2 is clear, we have logistic. If you have more than 2, then you might have to do a multinomial regression. If there is some order, maybe you can do an ordinal regression. But so far, if you are to do it yourself, and most of the softwares actually use this logistic. So once we have these probabilities, the matching starts. What's the point? Match a treated subject with one that did not receive the treatment. A heavy user with a non-heavy user, right? And hopefully, these two, in this pair, the 2 subjects are going to have comparable features. Now, how do we match? First of all, we do not do this by hand, okay? Everything is done in software, even by statisticians. The most common methods for matching are nearest neighbor matching, inverse probability of treatment weighting, or stratification. Now, nearest neighbor matching, 1-to-1. You take the groups, you take all your sample with the propensity scores, and you split them into treatment and control. You take subject 1 from treated, subject 1 that has a probability of 0.79, right, the score, and you look into the control group and try to identify a controlled subject that has a probability 0.79. Now, that's exact matching. Is it easy to do? Not so quite. So instead of exact matching, we usually allow a small difference. It's called a caliper. How large of a difference are you allowing between this treated and control? If ideally you want an exact match, but if you don't have exact you want a difference of 0.0001 or a difference of 0.001, or you want to increase that difference even more. How do you decide? First, start with a very, very small difference, because the smaller the difference, the better the matching. But if you see that you cannot find matches to all your treated subjects, then you might want to adjust this difference and to establish pairs. Another idea is to use inverse probability of treatment weighting. So for using your entire sample, you create weights. How do you create weights? Very easy. You do 1 divided by this propensity score matching for the treatment group, or 1 divided by 1 minus the propensity score for the untreated. You calculate all these weights for all the subjects, and in your outcome analysis, you just adjust for this weight. What's adjusting? Just include it as a covariate. Lastly, stratification or subclassification. Again, using your entire sample, you are dividing into equally sized groups based on the scores. So how can you divide? You can use tertiles that will divide your sample into 3 groups, or you can divide it into 5 groups, depending again on your sample size, because the more groups you create, you're going to reduce the sample size, and you might be problematic. Now, when you decide to do this stratification or subclassification, your comparisons are going to be within those groups. So for the first, let's say for the first quartile, you are going to compare the treatment and the control for that subgroup. Then you move to the second group. Usually you do not have an overall comparison unless in the outcome analysis you include that as the group factor as one of the covariates. But let's go back to one of the most popular method, nearest neighbor matching. 1-to-1. For one treatment, you select one control, but you can have one too many. What's one too many? For one treated subject, you can select 2 or 3 controls. When is that possible? Well, it depends. Maybe you do have more subjects in that reference group, so that's possible. But one thing to know, when you create these matched pairs, let's say 1-to-1, 1 treated, 1 control, you might have. You might use the entire samples, you might have matches for everybody, or you might not. And that's fine. Meaning, you can end up with 30, let's say you have a group that has 30,000 subjects, like in my example, and you have a reference group that has 2,000 subjects. When you're going to have the pairs, of course, the maximum numbers of pairs for 1-to-1 matching is going to be the smaller sample size from your group. Now, is this problematic in terms of throwing away the data? Yes and no. And personally, I would say, try to use as much data as possible, but I would not be so worried about throwing away the data, because when you are comparing groups that are highly imbalanced also induce high variability, you might not be able to detect an effect and the difference in outcome if one truly exists. So after matching, after we're trying to control for this observed confounding and variability, we already selected, we already narrowed down our area, so it might be even easier to detect an effect. Okay, so after we selected the pairs, now you have, let's say you ended up with 100 pairs, 100 treated and 100 controls. Your immediate thought would be to go and do an outcome analysis, compare the mortality rates or side effects or whatever you want to compare between these groups. Not yet. And a lot of people are skipping this step. And it's important because you need to assess the propensity score matching. Have you accomplished the goal? Are the groups comparable or not? How do we do that? Well, very easy. You do a bunch of t-tests and chi-squares. You look at the p-values and you're done. No, not enough. Why not enough? I'm not saying it's wrong. Of course, you use the test. You can even report the p-values. But it's not enough to assess the balance diagnosis, because we know very well that the p-values are that were heavily influenced by the sample size. And especially when you have huge imbalance, the chances that you have a highly significant p-value actually increase. So what do we do? How do we assess for imbalance? One, you can use some graphical displays. Between the groups treated and treatment and reference, do some histogram, do some cumulative density plots, and see if the distribution with respect to the variables, are they similar? Are they completely different? Do they, if you would overlay them, how do they look? Graphical display, of course, it can be also subjective. So in that case, to give a more standardized approach, we can use standardized differences. How is that? Well, very easy. For two groups, if you're comparing two groups with respect to continuous covariates, the standardized differences are given by D. On the numerator, you have the difference in sample means divided by a combination of the square root of the standard errors, standard deviations. Does that look familiar to you? The D? Maybe D as in Cohen's D? Maybe D as in effect size D? It's exactly the same thing. For binary covariates, the standardized difference is given by the formula shown below with the estimated proportions, again for two groups. Now, I mentioned D as in Cohen's D or effect size. That's exactly what it is. And remember that one of the rule of thumbs for Cohen's D, if you have an effect size of 0.2, that represents a small effect size. If you have an effect size of 0.5, then that's a moderate. Anything that's 0.8 and above, that's a large effect size. Let's think about this for a second. If we want our groups to be comparable, what kind of an effect size do we want? Do we want a large effect size, or do we want a small effect size? We want our groups to be similar, as similar as possible. What kind of an effect size do we want? Large or small? Small, absolutely. That's why a rule of thumb is when you take your groups, your initial groups before matching, you calculate the effect sizes, you can assess imbalance using this standardized difference D in absolute value is greater than 0.2, that indicates some imbalance between the groups. So what? If you see some imbalance with respect to a variable, then that's a sign that that variable should be included in your logistic regression, right, for estimating the propensity score matching. You're going to see, you're going to understand better in the example. In absolute value, what's absolute value? We don't really care about the direction, which group has more or less. So we only care about the magnitude. Now, after we did the matching, what we would like to see, if the matching actually achieved the goal, then all the standardized differences should be as small as possible. What's as small as possible? below, smaller than 0.20, smaller than 0.10. These are two common rule of thumb that you can use. This example shows you the graphical displays. On the left columns are the raw treated and control before matching. And on the right, we have the match treated and the match control. Can anybody guess what's happening here? Not guess, but say, what do you notice? Is the matching, was the matching useful in this situation, before and after, or not so much? Not so much. In the raw, we definitely, it's obvious that the two histograms of the propensity scores, notice the x-axis, are totally different. You would expect after matching to be more similar, or try to overlay. But in this case, but this is not the case in this example. So what would you do in this situation? I intentionally put this less than perfect example to see what would you do. Number one, go back. Maybe you didn't include enough covariates, right? Think of other confounders that you have not thought of and redo the matching. Try to try to be a little bit more stringent when you do the matching. Allow for even smaller differences. Maybe you were too tolerant in matching your treated with controls, and being too tolerant, you have not achieved this, the goal. So these are some situations. Okay. Let's say the matching worked after matching assessment, everything went well. The last thing and the ultimate goal was to do some kind of outcome analysis. You want to compare the groups with respect to mortality rate, side effects, whatever it is that you want to assess. One question is, what kind of analysis are you going to use? Are you going to use methods for match data or for independent data? Debatable in both cases. If you think about, right, you've done matching with respect to a lot of variables. So you can use, let's say, pair t-test. On the other hand, you could argue that the matching was not done based on outcomes, like in a case control, where you select on outcome and you assess on exposure. So there is no need to do any paired analysis. The literature is definitely divided. So I personally use independent analysis and independent tests, and I don't consider this to be a paired data, a matched data. Now, another way to do analyze the outcome, if you do not want to create pairs and go through all that nearest neighbor algorithm, you can do a regression analysis with your outcome as the outcome as the dependent variable, covariates, adjusting for all the propensity scores, all those probabilities that you had in the data. Weighting, if you use any weights. In subclassification, again, you can analyze your outcomes in each group that you had, or you can also include the subclass category in the model and an interaction with treatment. Okay. Now, in the outcome analysis, the question is, if you decide to do another regression to estimate the effect of some covariates on the outcome, what covariates should you include? Should you include the same covariates that you use for propensity score matching? Well, yes, if not interested in the coefficient of that covariate in the outcome model. Meaning, If you're not specifically looking for the effect, let's say, if you use age in your propensity score matching, if you are not really interested in assessing the effect of age on the outcome, then you can include that in the second model, in your outcome model. Doesn't matter. If you are particularly interested, you want to report that and make some inference, do not include. Why? Because you've already adjusted, you accounted for differences in your PSM. Last thought before the example is, do not forget to check for covariant imbalance. Oh, I'm sorry, forgot about the missing data. Very, very important. Missing data will come up at some point, and there are two different issues: missing data in the covariate or missing data in the outcome and treatment. If you have missing data in your covariates, the one that you're using for building the propensity score matching, it's problematic, but one way to go around it, you can discard that covariate completely. You have a high percentage, 60, even 40% of that covariate has missing values. You want to know, really, if you include it, it might do more harm than good. If you don't want to discard it, then you can categorize the variables and include an indicator variable for missingness. So let's say you have a variable with 2 categories. You can include category number 3 as missing and put all those 3 categories in your propensity score matching. So there are a couple of ways to go around missing covariates. If the missing values are in the outcomes or in those treated control, right, whatever that is, then this is a nightmare. First, the literature does not recommend doing any imputation. And if you think about it, it's very difficult. If you impute your treatment and control, you fit some models and you impute these missing values, then you would have to not only generate a lot of data sets and a lot of repetition to account for all this uncertainty, you might even end up with the wrong matching. So if you have missing in outcome or the treatment control, try not to use impute or stay away from PSM. Quick facts. Can PSM be used for longitudinal studies? What is longitudinal? At this point, everything is observed at one time point, a snapshot in time. Can we use PSM for longitudinal? Yes, we can. There are other advanced methods, and there is a lot of literature, meaning if you have some kind of a measure recorded repeatedly over time, that can be used. What is, yeah?
Is it possible to go to the example at all? To like apply, it's been 20 minutes, is it?
Absolutely.
If that's okay.
Yes.
The working example will put things into much more
Okay.
context.
Perfect. Okay. So, before the examples, I want to give you some links for software, how to do PSM. You can do it in R, you can do it in Stata, and you can do it in SAS. And on this handouts, you have the links, and the slides are going to be available on the website for BIRD. So the example. This is a study done in collaboration with Department of Surgery. And the retrospective study using information from American College of Surgeons National Surgical Quality Improvement Program. What did they want to do? They want to use PSM to create comparable risk groups in the laparoscopic and robotic cohorts with respect to demographics, comorbidities, and operative characteristics. Question: what are the groups that to be compared in this data set? What do we want, what are the groups that we want to make comparable and similar? The two groups, the treatment and the control, the treatment and the reference, are laparoscopic and robotic. Okay? We have defined the treatment and the control. Now, we want to make them comparable with respect to some covariates. What covariates are? What are those covariates? Demographics, comorbidity, and operative characteristics. Once they are comparable, we're going to assess the outcomes. You'll see mortality rates and all that. So PSM was used to make the groups comparable. Imbalance was defined as an absolute value greater than 0.10, and matching was performed using nearest neighbor algorithm 1-to-1. Text taken exactly from the paper. All perioperative variables with more than 90% of missing data were excluded from analysis, which, in my opinion, I think is common sense. And this is what we reported. Table 1 shows the patient characteristics before and after matching. Notice, unmatched comparison and matched comparisons. Let's focus on the unmatched comparison. Notice that we have 34,000 in laparoscopic and 1,700 in the robotic group. Okay? These are the two groups that we decided to compare. Now, they were assessed with respect to a bunch of variables, a bunch of covariates: age, sex, race, BMI, functional status, wound classification, underlying diagnosis. Variables that were related to this laparoscopic and robotic. Okay? Clear. Then we compared the groups with a t-test, the chi-square. We put the p-values, but we also put the standardized difference. Notice in the red quadrant, standardized difference, we have 0.06, negative 0.17. If you go all the way to the end, you see that the underlying diagnosis has a standardized difference of 0.25. This is problematic because we decided to use 0.10 as our cutoff. Okay? Now, after matching, after we used all these variables to do a logistic regression, we did the nearest neighbor algorithm. We look at the match comparisons. Now, what do you notice? At this point, we ended up with pretty much 1,200 pairs. N equals 1241, N equals 1241, right? Because we did 1-to-1. Did we throw away lots of data? Yes and no, because we did from the laparoscopic group. But look in the robotic. We sacrificed about 500 patients, okay? Now, in this case of an imbalance, 1,700 versus 34,000, that would have been pretty problematic. So 1,200, I think it's reasonable in terms of matching. So 1,200 laparoscopic and robotic. Again, we reported the descriptive statistics, mean standard deviation, and the standardized difference. What do you notice? On the second red quadrant, we have all the standardized differences are 0.10 and lower, which is exactly what we wanted. You will also notice, however, that some variables became more imbalanced, right? For example, look at the wound classification. We started at 0.04, and now we have a 0.10. Don't be alarmed. It is possible that the moment you're matching, you're going to create more or less imbalance. But as long as overall all the values are below 0.10 or 0.20, whatever you decide, then that is fine. So now, what are we going to use for the outcome analysis? Because at the end, we wanted to do 30-day post-operative complications for these groups. We're going to use the 1,200 pairs that we made with the matched, with the PSM, and compare them between the laparoscopic and robotic. Now, for this comparison, I used independent, two-sample independent t-test and Fisher exact test. What are the outcomes of interest? 30-day mortality, unplanned operation, all this post-operative complication. And this is it. The reference is there. You can use take a look and use as an example of how to report the results of PSM, how to check for diagnosis. I want to point two things before ending. Number one, I provided a SAS macro for checking balance. You do not have, we don't calculate this by hand, right? You have a list of 100 covariates. You're not going to check balance. There is a macro that calculates balance for both continuous and binary, and categorical variables. Also, to do the matching, you have SAS and R does this for you. For an extensive workshop on PSM, please look at Elizabeth Stewart's website. She actually has a Summer Institute course on PSM on several days, and the slides are some slides are taken from her presentation. This is me, Cody Chiuzan. Email me for questions. I provided the link to our resource, and you will find the PDF for today on this link. If you have any questions, if you have any suggestions for future topics, let me know or email me.